all working out over the break.
To finish attending, the person who discovered the error in Zoom at the last minute it was a very pleasant surprise when I got a phone call from Jenna, who, as you may have seen today, was just announced as the new executive director of the RASC. She's returned.
Super. Oh, yeah, that's
fantastic
great.
News.
Yes. Oh, that's amazing. Yeah. Okay, folks, we'll get things underway. So good evening and welcome to the May 5th meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. Welcome to our visitors, our guest speakers, and those visiting from other RASC centres. So we are recording this session on Zoom, and if you have any questions for the presenters, please use the Q&A box, not the chat box. We will be monitoring the Q&A box and passing those on to the presenter. A reminder too that your chat comments can be seen by everybody, so watch what you say. Raise your hand is disabled. If you do want to get our attention, please put something in the Q&A box and we'll be happy to respond to you. Okay. Robert Dick's saying, can somebody else, those who are online, are they hearing the audio okay? I've got one person who's not picking up the audio. Maybe get somebody to just type in the chat box. Certainly as panelists, we can hear it. Any of the participants hearing us at all? Yeah, okay. So other people have received the audio, so that's great, thank you. And so Robert Dick is having some issues with his audio right now, but it appears as though that's unique to you. So thank you very much, folks, for the feedback on that. So the RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and sky. Here is the order for things tonight. The introduction, Ottawa Skies. We've got Astronomy by Night. We've got Carina. You may recognize her name. She was the former editor of Sky News. She's got an exciting new project to share with us tonight. Got Kyle Reiter talking about the solar cycle, sunspots, flares, and CMEs. We have a 5-minute break with some AstroTrivia. And Jim Thompson's going to be talking about Astronomy Day and weather forecasting. He was able to forecast that the Astronomy Day was a no-go. The International Astronomy Day was a no-go as a result of all the wet weather we've been having. Anyways, and we have a bunch of really cool observation reports. Welcome to our new members for this month, Christopher, Tony, Nicholas, Douglas, Andrea, and Bojan. And we have 33 new members in 2023. And we always encourage folks to seek out a membership with the Royal Astronomical Society of Canada. The current membership rate is $103 for an adult, $97.50 for a family membership, and then $16.90 per adult, $9.20 per youth. And we also have a youth membership for those under 21 or under 25 if they're a student, and it's $62.40 a year. So what do you get for that membership? Well, locally, we have the Ted Bean, I'm going to need another coffee, I think, Ted Bean Telescope Loan Library, and we've been adding to that library recently, so I encourage you, if you want to try a telescope out, it's a great place to go. We do have the Stan Mott book library, and oops, I think I'm seeing Chris, it disappeared off my screen here. I don't know whether, got a little small picture in the corner. So maybe you can go back a slide. There we go. Yeah. So so we have the Stan Mott book library. Right now, that book library is locked up in the Canadian Aviation and Space Museum. And but we do have some out at our various houses. So if you're interested in a starting book in astronomy, please reach out to us. And we have our own private members observatory out on the far side of the Milliken Tail, the Fred Lossing Observatory, and we'll be hearing some more about that tonight. Okay, next slide, please. There we go. As nationally, you're going to get the journal, and the Observer's Handbook comes out once a year. And locally, we have our well put together Astronauts that comes out monthly with articles by our various members. Gordon Webster is the editor for that. And the main benefit is all the people that are part of the Royal Astronomical Society. It's amazing when we get together, particularly at star parties. And yes, we are planning to get together in person, have in-person meetings. We're working hard on that. I just don't have a concrete update at this stage in time, but this month things really started to move forward. Okay, next slide. It's Ottawa skies for May. Let's see what's happening in the skies in May this month. Well, tonight we have the full moon, obviously. And this full moon was known by early Indigenous peoples as the flower moon, because it's the time of the year when the spring flowers appeared in abundance. This moon has also been known as the corn planting moon and the milk moon. We have a new moon on the 19th of May. We had the Eta Aquarids meteor shower. Not great timing. They start Saturday night, overnight to Sunday, and we've just come off of a full moon. Best viewing time for that is after midnight. About 30 meteors per hour is the norm for the Eta Aquarids meteor shower. As you can see, the days are getting longer and longer as we move along, and these is the sunrise sunset times for the month. Mercury is at the greatest western elongation. So this is a good time to look at Mercury is just before sunrise on May the 29th. And you'll be able to see it just in the eastern sky. And these rise and set times are as they are in the screen there. When it comes to the elongations, either side of this date, you'll still be able to see Mercury before the sun rises as well. Venus is visible in the evening, as is Mars. Jupiter is visible before sunrise in the second half of the month. The first half of the month, it's rising and setting with the sun. And Saturn is visible before sunrise throughout the whole month. And Uranus is visible before sunrise in the second half of the month, and Neptune is visible before sunrise right now. And here's our cartoon of the month. If you've got a small screen here, you may not be able to read the text, but the text says set up for the meteor shower. You can see they're all looking in the correct direction. Okay, thank you. So I'm really excited to have Carina here. Let me just spotlight you. There we go. So Carina was a former editor of Sky News, and she's launched a new project, a new website that's Canadian in nature. And I'm going to turn it over to her. We mentioned and talked about this briefly last time. And Carina, welcome.
Thank you so much. I'll just going to share the presentation here. And we can get to, so can everybody see the presentation?
It's just loading.
Yep, should just say Astronomy by Night in black.
I just see the loading symbol. That's all I see.
Let me try something else to make it go a bit faster then. Let's try directly on the website. Okay, so I'll share the screen. Here we go. Does everybody see the website?
Yeah, that looks good. Yeah.
Perfect. All right, so we'll just forego the presentation slides. So hi, everyone. Thanks for this opportunity to present this new website. So what the presentation slides did include was a little bit of background before I get launched into what Astronomy by Night is. So I'm the former editor of Sky News and unfortunately the last editor of Sky News. When everything closed down, like a lot of people, I was feeling a bit down about the site and the magazine closing up. So when everything was closed up and we posted the last articles in the magazine and on the website, an idea had come to me to create a new website. So I sat with that idea for a little bit, and I thought there's a few things I'd need to make it go forward. I'm not sure if it's a great idea, but I did discussed that idea with the president of the RASC, Charles Ennis, and we discussed it for some time. He thought it was a great idea. It was really supportive, and eventually, many weeks later, I decided to go ahead with it. So Charles Ennis is actually one of our contributors, and so Astronomy by Night was born. It was born in large part, to fill up a space that Sky News was leaving behind. This is a website with a newsletter. It is not a magazine, a print magazine, or a digital magazine. So it's filling up some sort of space, but we wanted to ensure that there was a lot of Canadian content. It was done by Canadian contributors, but of course, there was also content coming from all areas of the world. So Astronomy by Night, in a nutshell, it encompasses similar elements to Sky News. Of course, we have a section on astrophotography, and we have a section to submit your photos. So I'll put that as the main highlight. There's a form, there's rules, easy enough to follow and to submit. And we publish those on a weekly basis. We have our winners, we have some information about their equipment and any notes they may have included. So for example, Benjamin Law was the runner-up for this week for his full solar disk. And some of the people, excuse me, I'm just coming off a cold. Some of them have actual notes that they want to leave. I apologize. So we've left those notes as well, along with the equipment. And for this particular week, we had an honorable mention because of the aurora that was visible, so widely visible. We've included an additional win. So once in a while that happens. Our photo judge is Dan Coos, who was actually one of the 3 judges for Sky News. And so everything you see written in this page is all from Dan. So he's the one that selects the photos, and he provides his background, his comments, along with a lot of background about what the picture is. Other things we're covering are basic news elements. So it's always fun to cover news. We'll give you as much as we can, information, videos. News is being done on a regular basis. We have a star chart. The star chart's being done in collaboration with Heavens Above. So they kind of provide a system. It's a website in Germany, actually, that kind of creates an old-fashioned website, but you're able to create an old version and a new version of the sky chart here, putting in where you're from, for example, and if you want it in black and white, if you want to create your own star chart, or you can create the old version, and they give you a black and white version too. So you can put in your date, your time, all those things. It's not quite Stellarium, but it's great if you want to have just a quick idea of what you're doing. We've also got some collaborations. One is with Clayton's Exploration Station, in which he will be doing some videos that are more family-friendly, kid-oriented, for the eclipse and other aspects related to astronomy that kids can create things. So we have a video here, and of course there's even a collection of the things you need to download, the information. So there's a lab sheet, all the information you need to download to do this activity with your kids, if you are grandparents or your parents that have kids. These are things we're testing out to see how they work with the audience we have. We'll be looking through Google Analytics to see what works, what doesn't, what works we'll keep, what doesn't we'll adjust, we'll either take out or replace. And that includes video interviews about what's going on in the world. For example, a recent conference that took place in Vancouver that is connected to telescopes, to groups in Africa, to groups in Australia, as well as Canada's potential participation. And so we've got information about all of that. So there's different things we're testing out. This week's sky, of course, we have that being called This Week's Night Sky. That if the name sounds familiar, it is. Chris Vaughn is the author of this, and he was previously a contributor for Sky News. So we'll be publishing these on a weekly basis. If you want to prepare your observing schedule. And of course, we have, like I said, news. We've got interviews about light pollution that we've done with NORLab. There are also some news that we'll be covering, little bits and pieces for different RASC centers. We'll be doing profiles, mostly astrophotography profiles. So we'll be getting different ones from different people, covering the type of how they got into astrophotography, what their angle is, why they're interested, the moment that they just got hooked on it. So for example, this talks about the background of Dan Coos, who's one of the photo judges, as I mentioned, how he got into that, how he became a judge. But we've also got one person from India who we covered as well, who spoke about how they got into astrophotography, the challenges they had to overcome in a group in India with lack of having any group to kind of help them out. So their situation, or this person's situation, was quite different from having a group like the RASC here in Canada, and how they managed to create a group and build on that and spread astrophotography in different areas of India. So different stories to share, and how they're doing in astrophotography, what they've won, how they've moved forward with their careers. In terms of columns, we've got 2 contributors right now. Hopefully we'll have more. One, again, is from Charles Ennis. He's covering world asterisms, big passion of his, and we really liked that in Sky News. Didn't want to lose that. So he has a column coming out every month. And so, for example, this one, he talks about what asterisms are, naming them, and of course, he gives some examples. And his next one, of course, will be coming out next week. And we have Samantha Lawler, who's studying Kuiper Belt objects. And so she goes into her research and explains exactly what she's doing, what they are, and how that research is moving forward. So we're looking to include more contributors in terms of their research, whether it's related to observing or other astronomy aspects. And of course, perhaps this will be a favorite for some people, gear and tech. So we have Alan Dyer, another name that should sound familiar, who is also previously a contributor for Sky News. He'll be doing our gear reviews, and he'll be covering some things on the upcoming eclipse in 2024 and the annular one as well. So you can expect more content from him as time goes, and he will be providing. So this one was a comparison. Some of them will be comparisons, some of them will be just regular gear reviews, as in a single gear review. I think that's about it. We also have a collaboration with the Actual Astronomy podcast. Some of you may know this podcast, so they do this on a regular basis. We've collaborated with them to write an article about podcasts they're doing once every month. So this one was about M51. You can listen to the podcast here, or you can read about the actual, like, in a nutshell, one aspect of that discussion, because it's about an hour long, 45 minutes to an hour long. So we just took out one part that we thought was the most interesting. And this one talks about the Earl who found the spiral in M51. So it gives you a bit of backstory about that, and why it's interesting. And of course, if you're really interested, you can listen to the entire podcast. So these are the type of collaborations we're doing. We also have a donation section. We are in discussion with many suppliers, vendors, manufacturers. They're all keeping an eye on what's going on with the website right now. Some of them are interested in putting in marketing dollars. We just need to boost our page views. So if you're interested, also you can sign up to the newsletter here. And of course, we have a contact form that you can reach us at. So everything's available here. The site's pretty clean. We may be changing CMS, so our content management system, which shouldn't really change the website too much. We'll be looking to replicate it as much as possible or exactly as is. Right now it's on WordPress. But this is essentially the site in a nutshell. So we'll be continuing. Main items are astrophotography, observing, and of course and news. Those are the three main ones that won't change. Everything else is subject to either grow, evolve, or be taken away, depending on how many people actually find the content interesting. And of course, you can always write to us and let us know what you'd like to see more of, what's interesting for you, and we'll be happy to find a way to implement more of that type of content. So that's the site and the website. Excuse me, that's the site in a nutshell. And I guess that's pretty much it. With the without the slides, it's a bit faster.
So Carina, how do we reach out to you? Is there a particular email that you prefer to receive comments, or is there's a contact us on the page?
Yeah, so we put that specifically through a contact us form.
Okay,
And
gotcha.
you can reach out. If it's just a comment saying, okay, I've had comments, oh no, thanks for creating the site. I love those comments. I don't respond to those so much because I get a lot of, there's a lot of back and forth between emails and interviews and such. If you have a specific question, I'm always happy to answer those. So feel free to reach out. And like I said, if you'd like to see something specific on the website, I should also mention very clearly that this is a side project. We are testing it. So we are seeing how it goes. I want to give it a year to survive, but every few months, we're really going to be looking in depth, and we're already looking and watching the numbers, but we're giving it the time to grow. We've spoken to different sales reps to get opinions on how long it could take before we get marketing dollars, things we need to do. And of course, I worked in the magazine industry for a long time. I haven't just worked for Sky News. I worked for other magazines before. Different industries, but the gist is similar. So we know what our timeline is to build up and when things should start working out, so we can get those marketing dollars to pay people like Alan Dyer, Chris Vaughn, Dan, previous Sky News contributors, and others. All the marketing dollars and donations do actually go directly to the site to ensure its maintenance and just for the contributors. So that's really what it's for right now, and for a long time to come. So our goal is to see this grow and evolve if people like it. And if not, that's fine. We'll find another home for it. So, but hopefully, really, it grows in to really take up a nice space in the Canadian amateur astronomy community.
So we have some questions that popped up here, Carina. First one from Edward Brown: does the website have night mode?
You know what? That's a great question. It did have night mode. We took it off just probably 2 days ago. There's a bug in the back end of the CMS in WordPress, and so it's not visible to anybody looking at the site, but it actually appears on the back end. And so that's a problem for how we're hosting this. Not problematic to you, but problematic to us. So we actually took off night mode as one of their suggestions. We don't think it's changed anything, and if it hasn't, we'll just put it back. Either way, night mode will eventually reappear.
Okay. So from Mick Wilson, he's our webmaster for the Ottawa Center. He says, we're about to restructure our site. How can we best plan to interact with Astronomy by Night? For example, channeling our meeting content, speaker presentations, etc. And Chris said, will you be promoting local astronomy events? Should we tell you about our upcoming public star parties?
The first question, I'm not fully sure how to answer, but you can feel free to reach out to me and we can discuss that. I'm not quite sure how to answer that unless you have more examples of what you mean by that first question.
Well, just so we can seamlessly sort of point people from our website to your website, integrate it, and so on. I think that's what Mick is trying to say.
Okay. Let me give that some thought, and I will send those comments to Dave by email.
Okay, sure. That's super. Yeah, and I can put Mick in touch with you.
Perfect. And thank you for that question.
Okay.
And so for the star parties, yes, by all means, please share your star parties. I've had some centers share them. I would love to put them all up in one list, but right now, if I can't get them all, I do want to promote that. I think everybody should have that information. The other thing is that for example, for the Ottawa Centre, if you have any interesting events coming up, feel free to put me in CC. Some things I will let go. Some things I might say, hey, that sounds great. I'd love to do an interview about this. Or so you never know.
Okay.
I'm always
Yeah,
happy
no,
to poke.
okay. Well, no, that's great. We'll certainly keep you up to date on what we're doing here. I don't see any more questions. Mick did pop his email into the chat there if you want to grab it, Carina. That's for the question about the website integration.
Perfect.
But I will
Thank you.
I'll send you a separate email as well.
Sounds good. So, great. So in that case, if there's no more questions, I would say thank you for the opportunity to present this website. And please don't be shy to let me know what you do like about it and if there's anything you don't.
Okay, and you encourage donations to support the. Obviously, this is not a free venture here. There is some cost to keeping the website and everything else going.
I would love for it to be free. It'll be about several months before we can get marketing dollars because we need a certain amount of viewership. However, I should also mention that we are in discussion. We're thinking about launching a potential astrophotography contest. And so if we do that, we've already spoken to some suppliers and they're willing to donate a telescope for this. So there's things coming up that we'll be organizing, getting in touch with to help really spread the word and get that out. If you like the website, then I'd say if you're comfortable donating, please go ahead. There's no pressure though, but it would help us to pay our contributors.
Absolutely. Okay, well, really appreciate your time tonight, and I'll encourage folks to give you feedback, everybody to visit the website. And it's certainly on the when I do my astronomy outreach, I've now added this to my web links for people to visit. So thank you very much, Carina. Really appreciate
Thanks
it.
so much.
Thank you.
Thanks.
Okay, so I'm going to turn it over to Kyle here. He's going to share his screen.
Sure. Okay. Let me get this shared.
Looks good.
Okay. Good evening, everyone. My name is Kyle Reiter. I'm a space weather and ionospheric physicist with Natural Resources Canada. Previously done my PhD at the University of Calgary, looking at the impacts of space weather on ground-based systems, looking at power transmission networks. But today I'm going to be looking at the solar drivers of space weather, giving a little bit of an overview of how activity on the sun can sort of propagate through the solar system and cause sort of beautiful auroral displays and cause all sorts of different sort of physical impacts visible here on Earth. So as Canadians, I'm sure most of us are familiar at some level with the Northern Lights, maybe not seen from this perspective here. This is an image taken from the International Space Station and isn't actually of the Northern Lights. It's an image taken of the Aurora Australis, or the Southern Lights. There's an aurora associated both in the Northern Hemisphere and the Southern Hemisphere. And we can think of aurora as kind of an indicator of space weather activity occurring on Earth, where we're seeing more, where we're seeing aurora where we wouldn't normally expect to see it. And if it's more intense, or we're seeing sort of brighter displays of aurora, that can be indications of space weather activity occurring. So what exactly is space weather? Space weather is kind of an umbrella term. It encompasses a set of physical processes that start on the sun and propagate through the solar system to impact the Earth's environment, activity on Earth, as well as activity in space around Earth. So this is sort of an artist's rendition from NASA showing sort of various types of solar activity on the sun. You can see these sort of big clouds of gases coming off. These are coronal mass ejections, these big loops, these filaments and prominences, and you can see bright spots associated with active regions on the sun, all sorts of activity going on. This activity propagates through the solar system and interacts with the Earth's magnetic field. And so we can see a bit of an artist's rendition of the Earth's magnetic field here as well. These sort of loops that we can see extending from the poles and from one pole and looping back around to the other one, kind of like a sort of a bar magnet's magnetic field. So this is the Earth's magnetic field, or geomagnetic field, as scientists will often call it. The impacts of space weather that we can see on Earth can be quite varied. They can be very minimal effects, things like static in your walkie-talkie or very small voltage fluctuations in a power transmission line, but they can also be quite significant. This can range from everything from sort of multi-hour power blackouts to problems with radio wave propagation for sort of high frequency radio communication. It can also cause all sorts of problems with satellite operations, including satellite orbit problems, losing orbits of satellites. We have a little bit of a video coming up showing you a problem that SpaceX had with some of their spacecraft last year as a result of a geomagnetic storm driven by activity on the sun. So space weather is all driven by the sun. What does the sun exactly look like? What are the layers of the sun, and sort of what is the normal activity on the sun look like? So the source of the sun's energy is the hydrogen core, which makes up about half of the sun's mass. This is shown here in the center of the cutout. Outside of that, we can see this radiative zone, where the energy emitted from the core of the sun diffuses out, and this can take a process of millions of years for this energy to diffuse out from the core of the sun. Outside of this radiative zone, we have a convection zone, and this convection zone is what causes the sun itself to have a magnetic field. And as I'll talk about in a little bit, the magnetic field associated with the sun is a driver of a lot of the activity that we associate with space weather. So we get these sort of currents forming in this convective zone associated with electrical currents, as well as associated with thermal currents. And since the sun is made of a large amount of electrically conducting gases, the motion of these electrically conducting gases in this convective zone gives rise to a big magnetic field, and the sort of structure of that magnetic field can change over time. Outside of the convection zone, we have the photosphere, which is sort of the innermost visible portion of the sun itself. And outside of that, we have the chromosphere and the corona at the very outside, or at the outermost portion of the sun. So we can see a couple of different types of activity associated with space weather shown here in the cutouts on our sun diagram. We can see some sunspots and some flares, but there's all sorts of activity associated with space weather arising from the sun. So how do scientists look at the sun? How do we characterize activity on the sun? What are the sort of instruments that we use to observe different types of solar activity that can give rise to space weather impacts? So here we have a selection of different images taken of the disk of the sun, I think from a couple of weeks ago. This is taken from solarmonitor.org if you're interested in looking at them yourself. They also have some images of some sort of processed images looking at coronal holes and so forth. It's a very interesting website if you're interested in looking at sort of the drivers of space weather. If you want to see, coronal holes as they develop and move across the sun, or if you're interested in looking at different sunspots and so forth. So we as scientists have a number of different instruments, a number of different spacecraft, which take pictures of the disk of the sun at different discrete wavelengths. And these different wavelengths correspond to different emissions from the sun. And we can use them to identify different features on the sun, such as coronal holes, these sort of darker portions of the sun, or to identify the development of solar flares, which are brightenings on the surface of the sun. We can also look at the magnetic field or changes in the magnetic field on the surface of the sun itself. We can see these sort of white and black portions of this image seen here in the top left. So the white portions of this image correspond to magnetic field lines that are coming out of the surface of the sun, and the black portions are magnetic field lines that are traveling into the surface of the sun. And these are associated with active regions on the sun, which can be the source of solar activity, which can drive space weather on Earth. So we not only have very high-tech ways of looking at the sun, we also have relatively low-tech ways of characterizing the surface of the sun. We have these things we call synoptic maps, which are essentially projections of different ways of imaging the sun onto a large surface, which observers then take pencils out and actually sort of sketch out different features on the surface of the sun. So we can see here, this sort of hashed line here in the middle corresponds to a coronal hole, which I'll talk about in a little bit. And we have, other little black dots corresponding to sunspots and active regions. So this particular synoptic map is taken from the Space Weather Prediction Center in Boulder, Colorado. But there are a number of different institutes all over the world which regularly, daily, make these images of the sun. And they're useful because they provide us with a sort of historical archive stretching back years and years, which lets us look at, okay, on this particular day, what were we seeing on the sun? What is the snapshot of the sun's activity? We can compare that looking back, and we can look at also the impacts that these various types of activity have on our Earth environment going forward from that as well. So they're an interesting snapshot in time. They give us an idea of what the sun's looking like at that given point in time. So what are some what exactly does the sun look like? It's a very dynamic and active body. It's not static whatsoever. The surface of the sun itself is very complicated. It's constituted of these electrically charged conducting gases, and similar to the Earth, as I mentioned before, has its own magnetic field. So these gases are constantly in motion, and as a result, also the magnetic field seen at different portions of the sun is constantly moving as well. Different portions of the sun can have intense more intense magnetic field strengths associated with them. We sometimes call those active regions, and these can be the source of different types of solar activity, which can drive space weather. So one type of feature that you might see on the surface of the sun is a sunspot. All this is a darkening, an observed darkening of the surface of the sun, and this is associated with a cooling of that portion of the sun. These sunspots can be about 2000 Kelvin cooler than the surrounding area of the sun. And the reason why they're so much cooler is because of the magnetic field structure associated with those portions of the surface of the sun. The magnetic field is so strong in these portions that the heat from the inner portions of the sun is prevented from reaching the surface, resulting in this cooler region of the sun. And we see this as a sort of darkening of the surface of the sun. Sunspots are of particular interest because lots of different types of solar activity can arise from regions associated with lots of sunspots. And the occurrence of the number of sunspots is not uniform over time. It varies with a sort of an 11-year period. And I'll be talking about that in a little bit because that's the solar cycle. And that's where we're going to be going into a solar maximum, a period of heightened levels of solar activity, of heightened numbers of sunspots. So to give you an idea of how the number of sunspots on the sun can change over time, on the left-hand side from 2011, we have a quiet sun where we can only see a handful of sunspots. Taken here is a sort of intermediate portion of a solar cycle taken from earlier this year, from March 25th, and we can see that as we're heading into a solar maximum now, we have more activity occurring on the sun. We have higher numbers of sunspots associated with this sort of more active sun. And then we have a picture here from 2001 from a solar maximum where we can see massive regions of tons of high densities of sunspots. We can see lots of sunspots all over the disk of the sun itself. So how different is the rate of occurrence of sunspots over time? We can see here that we've tracked over the last several hundred years the occurrence rate of sunspots seen on the sun. and the associated solar cycle. So there's an 11-year period to the solar cycle, which corresponds to the number of sunspots that we can see on the solar disk at any given point in time. So solar maximum, which you may have heard about in the news, associated with, bright sort of displays of aurora and solar flares and all this kind of stuff. Solar maximum is just the point in time for that particular solar cycle where we see the highest number of sunspots on the sun. So we can see a previous solar maximum from the previous solar cycle here, stretching back over many periods, over many solar cycles. And then correspondingly, solar minimum is just the period in time associated with the fewest numbers of sunspots associated with fewest number of sunspots seen on the sun. So as I've mentioned, the sun is an incredibly dynamic celestial object, and that is reflected not only in the number of sunspots that we can see on the sun, but also the regions of sort of intense brightness, the structure of the sun itself. We can see changes as we go from solar minimum here from 2010 through time, all the way through solar maximum here, seen in the middle of our screen, back to solar minimum again. So we can see over this 11-year solar cycle, there's a significant variation in the amount of activity that's occurring on the sun. Sunspots are sort of one of the principal ways in which we characterize the solar cycle and characterize the amount of solar activity occurring on the sun, but it's not the only way. One last thing before we move on to other types of solar activity, not only is the number of sunspots occurring on the sun sort of variable over time, but also their location on the disk of the sun itself changes with the solar cycle. So if you turn your head kind of to the left here, you can see what looks to be a sort of a series of butterfly wings. And this is we call a butterfly plot or butterfly diagram, which shows the occurrence rate of sunspots at sort of different latitudes on the solar disk. So when I say latitudes, the top and bottom portion of this plot here correspond to the poles. So the top and bottom part of the solar disk that we would see, and the middle here corresponds to just the middle of the sun itself, the equator of the solar disk. So we can see as we progress through a solar cycle that not only the number of sunspots changes, but also the location where we're seeing sunspots moves from sort of more polar regions towards the equator. And this is not only interesting, but it's also important for characterizing and predicting the sort of the impacts that solar activity associated with these sunspots could have on Earth, on predicting the types of space weather, or the impacts of the solar activity could have on our Earth environment. So just to give you a little bit of extra context here, Canada actually provides a very useful and very internationally used observation of the solar cycle. So this is the F10.7 Solar Flux Index. And what this is a measurement of the 10.7 centimeter radiation coming directly off of the sun over time. And this is taken from the Dominion Radio Astronomical Observatory in Penticton, which you may be familiar with. They have this F10.7 telescope there, which measures this 10.7 centimeter flux over time. And so you may be looking at the x-axis, the bottom axis here of this plot, and being a little bit confused as to exactly what it's showing, what a Carrington rotation is. A Carrington rotation is just a rotation of the sun, just like the Earth has a day-night cycle. So over the course of one day, the Earth is rotating around. The sun has a 27 and a bit sort of period to its rotation. And that corresponds to this sort of Carrington rotation number. And so we can characterize the solar cycles itself by the amount of 10.7 centimeter solar radial flux that the sun is putting out. And this is an important characterization of solar activity that Canada has been providing internationally for many years now. It's principally run by the National Research Council. So again, out of Penticton, very useful scientific instrument that Canada has been providing to the world for many years.
We have a question here.
Oh, sure.
Okay, from the graph showing the solar cycles over hundreds of years, is there also another variation over 110, 120 years? It seems the maximums are lower over that long period.
Yeah. So there are there's a lot of research that's been done over many years into sort of the structure and the not only the 11-year structure of the solar cycle, but the longer period structure of the solar cycle. So yes, there's an additional longer periodicity to the level of activity seen on the sun. There's not only a sort of 11-year solar cycle, but there are longer, 100+ year cycles in terms of how high the maximum is and how low the minimum is associated with each solar cycle. And there's a lot of statistical modeling that's been done looking at this, hundreds of years of data that goes into trying to predict the magnitude of future solar cycles as a result of that. So yeah, I have a slide near the end that kind of shows what the current status of solar cycle prediction is and how it kind of lines up with reality. We'll see how well scientists are doing in terms of sort of overall predictions of solar cycle activity.
Okay, thank you.
No problem. Just to go on to a new type of solar activity, not just sunspots, we also have solar prominences or solar filaments. And this is an image taken from, I think, March 30th of 2010, a sort of zoomed in portion of an image taken from the Solar Dynamics Observatory, which is a spacecraft that one of the spacecraft that NASA operates, which images the sun. But you can see this large arc of ionized gas here extending from the surface of the sun, and that itself is a prominence. It's just this arc of gas which extends outside of the surface of the sun. If we see them outside the disk, as it is here, extending beyond the disk of the sun, we call them a prominence. If we see them on the disk of the sun itself, we call them a filament. And they can be associated with expulsions of these ionized gases as well, in which case they become a coronal mass ejection. One type of coronal mass ejection, which is this sort of output of large volumes of electrically conducting gases into the solar system, can come from solar prominences and filaments. You may have seen some news earlier this year about a particular solar prominence. A lot of talk about sort of a solar polar vortex, and I hope the animation here is showing okay. It kind of depends on how good my internet connection is as to how well it's going to show up. But in sort of the polar region of the sun, we can see the development of this prominence here, this portion of plasma, this ionized gas extending from the surface of the sun and sort of circulating around the pole of the sun itself. And a lot of different news articles were written about, what exactly is happening here. People saying the sun has broken and, that there's a sort of, the sun is operating this way that we don't understand. And that's somewhat true and somewhat not. As I mentioned, solar prominences and solar filaments are regularly occurring, and they're a known phenomenon on the sun. This particular prominence, some of the activity associated with it, the sort of circulation around the pole, is going to be associated with a particular physics associated occurring at that sort of polar region at that point in time. And we don't have a good characterization of why it's flowing in this way. And a scientist had tweeted about this, talking about this sort of solar polar vortex, which kicked off all of this sort of reporting on the topic. So if you're wondering about, if you'd heard about this earlier this year and were wondering what it is, the answer is it's a prominence, and the exact mechanics of why it's circulating in this way, we don't know, but it's not exactly a sort of new type of activity that we've never seen before. Another type of activity on the sun is a solar flare. As I mentioned before, the magnetic fields associated with the surface of the sun, and especially around active regions and sunspots, can be quite complex and can become very kinked and twisted in and around these regions. This sort of twisting of the magnetic field in the regions around active regions can result in the storage of energy inside the magnetic fields there. And this energy can be released explosively. This explosive release of energy can be seen sometimes as sudden brightenings on the surface of the sun with emissions of large numbers of X-rays or higher numbers of X-rays associated with it. And we can observe them as brightenings on the surface of the sun, seen here or seen here. The radiation, the X-rays that the sun emits as associated with solar flares take about 8 minutes to arrive on Earth, the same as any other light being emitted from the sun, and can interfere with or can produce a variety of different impacts on the Earth. So we can see sort of increases in density of ionization in the upper atmosphere, can impede the movement of radio waves in the upper atmosphere as a result. I'll talk a little bit about that further in a second. But I want to talk about how we actually quantify these solar flares. So we can see here on the screen a snapshot from June 2015 showing the X-ray flux over a course of about a week or so. And we can see that it's changing and spiking up in a couple of portions here where it's getting quite high. And these are associated with these larger solar flares observed on the surface of the sun. We characterize solar flares by a sort of a letter and a number. So we go B, C, M, X in increasing order of, or increasing X-ray flux amount. So we can see on the left-hand side of the screen, the numerical number of X-ray flux associated with the solar flares, and on the right-hand side of the screen, the letter associated with the classification of these solar flares. So the X-class solar flares are the highest magnitude and be associated with the sort of the largest space weather impacts that we can see with solar flares. In addition to solar flares, we have coronal holes, which are regions of the sun with magnetic field lines that are open, which don't loop back in on themselves, but in fact extend out into the solar system. And we can see them as dark regions on the surface of the sun. And these regions of open magnetic field lines are also associated with high-speed streams of solar wind or plasma. I'll get into defining exactly what the solar wind is in a second, but basically higher velocity streams of charged gases come from these coronal holes in these regions with open magnetic field lines. And these higher speed streams of plasma can interact with the Earth's magnetic field again and trigger space weather activity. So we can see two different types of coronal holes here, one seen more closer to the pole on the right-hand side, so this large polar coronal hole, as well as we can also see sort of more thinner, more equatorial, although extending towards the pole as well, coronal hole. So they can have a number of different shapes and sizes, and again, associated with open magnetic field lines and high speed streams of plasma that extend into the solar system. Another type of solar activity is coronal mass ejections. So as I mentioned before, these are these big eruptions of conducting gases from the surface of the sun. They can be associated with filaments, but they can also be associated with solar flares and active regions. You'll often see news articles talking about solar flares shooting gases out into the solar system. That's not strictly speaking true. It's a coronal mass ejection that is resulting in charged gases, or large volumes of charged gases extending into the solar system. And we can see a couple of different examples seen here where these are images taken from the Solar and Heliospheric Observatory from NASA and ESA. And we can see a couple of videos here of an example from earlier this year with a couple of different fields of view. So looking at a couple of different sort of radii or around the sun. So you can see the sort of expulsion of these charged gases out from the surface of the sun. Now, for some coronal mass ejections, for some types of solar activity, we may also see other types of impacts. This is the same type of image as I showed in the last couple of slides, but we can see all of these white pinpricks everywhere. These are associated with solar energetic particles. These are very energetic protons that are accelerated either by coronal mass ejections or by other activity on the surface of the sun and travel quickly towards Earth. They can interact with spacecraft. They can interact with the Earth's atmosphere to increase ionization and again cause problems with high frequency radio communications as a result. One thing that you might notice here is that there's these images that I've been showing over the last couple of slides have a couple of weird features to them. There's this kind of this disc in the middle and sort of a darker portion extending out towards the edge of the image. It almost kind of looks a little bit like kind of a selfie stick, but it's a bit of a reverse selfie stick in a way. Essentially, in order to avoid the sun, the brightness of the sun itself overwhelming all of these images, there's a small arm from the edge of the camera that's pointing at the sun that then has a little disc on it that blocks out the sun itself so that we can see more easily the corona around it. And so these are called coronagraphs, so that we can characterize both coronal mass ejections and also see solar energetic particles due to these sort of white counts that we can see, bright counts that we can see on the imager as well. So I've talked about a number of different types of solar activity. We can see here a couple of different solar cycles. These here looking at number of sunspots over solar cycles. So again, the sort of the brightest portions, not the brightest portions, the portions in time associated with the largest number of sunspots are solar maxima, and then the lowest number are solar minima. We can see that higher numbers of solar flares are associated with higher numbers of sunspots. And additionally, higher numbers of coronal mass ejections are associated with both of them. The same also with solar energetic particle events or solar proton flux. Sometimes we characterize these events by their solar proton flux. So all of these activity or all of these types of activity are interrelated. They're all related to the overall level of solar activity occurring at any given point in time. We can observe them directly on the sun with a number of different spacecraft, a number of different observing locations. We can also model their impacts on the broader solar system. So we have a few different sort of simulation or cut-throughs of simulations that were conducted at Natural Resources Canada. The top two plots here are looking at the density of plasma extending out from the sun associated with a coronal mass ejection coming up. That this is, I think, from a couple of weeks ago. If you saw a bunch of news articles about the aurora, this was the event that was associated with that. So we can see this coronal mass ejection extending out with higher densities of plasma, of these charged gases coming out from the sun. We can also see that the speed associated with this coronal mass ejection is higher than the ambient speed of the solar wind, of the charged plasma that's sort of ambiently being exuded from the sun itself. So the top two are looking at sort of a top-down view of the orbit of the Earth around the sun, and this is a side view here. So we can see that not only is the sort of direction relative to the Earth and sort of the Earth's orbit important, but also how close to the pole the sort of activity on the sun is occurring is also important for determining whether or not the plasma that's emitted from these coronal mass ejections or any other type of activity is going to directly interface or interact with the Earth itself. So we have, in addition to sort of Earth-based and Earth-orbiting observations of the sun, we have some ways of characterizing the solar wind, the sort of plasma that's flowing out of the sun towards the Earth, sort of directly of measuring sort of the speed, the density, sort of different magnetic properties associated with the solar wind as it's traveling from the sun to the Earth. There are a couple of spacecraft located at the Lagrange point, which is a sort of gravitational neutral point where it's easier to put spacecraft that uses less fuel and less energy to maintain them at that orbit. Essentially, we have Discover, which is one of these spacecraft, and also have ACE, which is a previous mission. Both of these directly measure various properties of the solar wind as it's traveling from the sun to the Earth. And they give us about 30 to 60 minutes worth of notice as to exactly what the properties of that solar wind is going to be. So this gives us a little bit of an idea of what the data that we get directly from these spacecraft looks like. This is looking again at the event that we had a couple of weeks ago where we had that coronal mass ejection. It interacted with the Earth's magnetic field and sort of caused these auroral displays that we saw, as well as various other space weather impacts. So the top plot here is showing the magnetic field associated with, or the magnetic field measured by these spacecraft at this sort of partway point between the sun and the Earth. We can see the overall magnetic field in black and one direction, these sort of up and down relative to the sort of the orbit of the Earth around the sun direction of the magnetic field shown here in red. The reason why we're concerned about that direction of the magnetic field is when we see a prolonged period of a negative or a downwards direction of the magnetic field, that makes it favorable for the development of geomagnetic activity as a result of interactions with the solar wind. That comes from sort of the structure of the Earth's magnetic field. I'll talk about that in a second, but we can see that there's a sort of disruption, this disruption of the sort of the steady state solar wind associated with the arrival of this coronal mass ejection, the sudden jump and the sudden increased variability associated with the arrival of coronal mass ejection, not only in the magnetic field, we can see that in the density of the solar wind as well as the speed. There's a sudden uptick in speed associated with this higher speed coronal mass ejection traveling from the sun towards the Earth. So this here is the Earth's magnetosphere. The magnetosphere is just the area around the Earth dominated by the Earth's geomagnetic field. So it looks kind of like a bar magnet with sort of poles here in the north and south and sort of magnetic field lines extending from one to the other, but it's distorted, and it's distorted by its interaction with the solar winds. We can see it's kind of blown back by this interaction with the solar wind. The pressure from the solar wind actually distorts the shape of the magnetic field of the Earth. And depending upon the orientation of the solar wind and its interaction with the magnetic field, you'll get different levels of sort of injection of energy and charged particles into the magnetosphere. And these have a number of different impacts. One type of impact that we can see in and around Earth are spacecraft impacts. We can see problems with electronics on spacecraft associated with energetic particles, both solar energetic particles as well as energetic electrons that can get accelerated within the Earth's magnetic field itself and interfere with spacecraft operations. And the other type of interference with spacecraft operations that we can see, as we saw last year with some Starlink satellites from SpaceX, is increases in satellite drag. And this comes from basically excess heating in the upper atmosphere associated with the aurora and the large electric currents associated with the aurora that actually expands the upper atmosphere so much that the drag on low orbiting satellites increases. And this can cause problems when you're launching a set of spacecraft, a set of satellites, right when you have a geomagnetic storm, which is what happened last year with SpaceX. they got their spacecraft into an initial low orbit, and they were going to maneuver them into a slightly higher, more stable orbit. But the increased drag kept them from being able to adjust the attitude, the position, the orientation of their spacecraft to get it out of that low orbit. And many of them ended up burning up as a result, as we can see here in the animation on the right-hand side. There are a number of other impacts on high-frequency radio propagation as a result of increased geomagnetic activity. We can see here the auroral oval, which is the sort of region associated with the brightest and most regular auroral displays. This is caused by the precipitation of energetic protons and energetic electrons from space down into the upper atmosphere, which then causes emission of light from the elements that and molecules that those precipitating particles interact with. Additionally, this causes problems, this sort of increased ionization of the upper atmosphere interferes with the propagation of high frequency radio. It can also cause problems with GPS and GNSS positioning as a result of the changing density of the upper atmosphere. Not only do we have sort of upper atmosphere impacts, we can also have impacts on power transmission networks. So we can see here a plot of the sunspot number over the last several decades, and then also some events where we had power irregularities associated with space weather impacts. So of most interest to Canadians here is a 9-hour blackout of the Hydro-Quebec system in March of 1989, shown here. With a very large geomagnetic storm that was observed at the same time, driven by a couple of coronal mass ejections up from the sun, but also a number of other power transmission network associated impacts over the last several decades, often occurring during solar maximum, where we're seeing increased amounts of solar activity. So for forecasting space weather, what kind of warning do we have about activity? What are the sort of time periods over which these sorts of activities occur? For solar X-rays associated with flares, they take about 8 minutes to arrive, and their impacts occur over sort of minutes to hours. Energetic particles, like those solar energetic particles that I mentioned earlier, they take tens of minutes to arrive at Earth and can have impacts on the order of hours to days. And this can be impacts in terms of the interference with high frequency radio propagation. Coronal mass ejections and coronal holes take a bit longer. The speed at which these plasmas move is slower than the energetic particles and X-rays, but they can have longer periods of impacts, hours to days for both of them. Here in Canada, with Natural Resources Canada, we have a number of different ground-based measurements of space weather impacts or ways of observing potential space weather impacts in Canada. We have a network of magnetic observatories which look at the Earth's magnetic field and how it changes over time and how those changes are associated with space weather. We also have a network of rheometers which measure the ionospheric, the upper atmosphere density and how that changes associated with space weather activity, as well as GNSS receivers, GPS receivers, basically, which can look at sort of positional anomalies associated with changes in upper atmosphere density, associated with a whole with many of these sort of space weather impacts that I've mentioned before. So we do all of this from the Canadian Hazards Information Service, which I'm a part of. We have the Geomagnetic Laboratory here in Ottawa, as well as the Canadian Space Weather Forecast Center, which is an operational center which looks at monitoring space weather, potential space weather and impacts to the Canadian public, as well as to industry and government as well. If you're interested, our website is spaceweather.ca. We also have a Twitter where we release alerts about potential or ongoing geomagnetic activity that could be associated with space weather. and can give you a good idea if there could be a good auroral display in your area at the time, assuming it's not cloudy. So going back to sort of the sunspot number and kind of where are we now, we can see sort of a time history of sunspots from the last several years here over the last solar cycle. This is taken, I think I took this from a couple weeks ago. And then this is a comparison to a number of different scientific models of what we expect the next solar cycle to look like. So this envelope of this sort of shaded area is the sort of uncertainty region of what the different models are saying the number of sunspots could look like over the next solar cycle. And as we can see, we've already kind of overblown it a little bit. Predictions of sunspots is still an ongoing and active area of research, and scientists from across the world are actively looking at improving our ability to forecast solar activity over coming solar cycles. There are a number of active sort of bids or bets going on as to which model is going to be most accurate. I think there's probably not any money involved, but probably a couple of beers. So yeah, just in conclusion, space weather is a collection of physical processes and driven by activity on the sun and can affect human activity, human infrastructure in and around Earth. And that solar activity varies over an 11-year solar cycle. Canada is particularly vulnerable to space weather impacts, but we also have a really great vantage point for viewing not just the aurora, but scientifically observing the sort of physical processes that drive space weather, as well as driving the aurora and other processes in our region. So thank you so much. Thank you for your attention, and thank you for having me this evening.
Thank you, Kyle. It was most fascinating. Another question for you from Mick Wilson. Are
Sure.
there any collaborative programs in which amateur citizen scientists can contribute, visible or radio astronomers can contribute to the alert systems?
Yeah, so for our operational sort of forecasts, we don't currently have a way of integrating amateur observations, but there is a very strong citizen science initiative in Canada that is looking at developing, sort of pushing forward the envelope of our understanding of the aurora, our understanding of space weather. You may have heard of Steve, of sort of a auroral related phenomena that is sort of a brightening that's associated with the aurora. I don't believe it actually technically is the aurora, but that was a citizen science initiative out of Alberta that was driven by observations of this sort of strange lights that we hadn't seen before, that was brought to the attention of scientists at the University of Calgary and elsewhere, and a whole bunch of very productive research has come out of that. I believe Aurorasaurus is a US-based citizen science aurora observation platform, like where you can submit photos of the aurora and so forth, which can be useful for tracking where the northern lights are occurring and sort of looking at structures in the northern lights as well. So that would be one place you could look for if you're interested in helping push forward this sort of auroral science.
Okay, well, thank you very much, Kyle. Fascinating presentation.
Thanks.
Okay, so Chris is just going to get the slides restarted here. And I'm just going to try to spotlight myself if I can. There we go. So here we're going to take a 5-minute break. So here's the question for a question of the month. What direction does the Jupiter red spot spin, clockwise or counterclockwise? And how long does it take to complete a cycle in terms of Earth days? So think about that over the next 5 minutes, and we'll see you then. Okay, folks, hopefully you've all had a bit of an opportunity for a break. We're going to move into the second section here. So I'll get Chris to bring up the answer to the trivia challenge. I didn't see anybody type in the answer there. It goes counterclockwise and it takes 6 Earth days to complete its rotation. So that's the red spot, the big storm on Jupiter. So let me just go here. So next up is Jim Thompson. So Jim, I'm just going to spotlight you. There we go.
All right. Thanks, Dave. So I'm just going to talk briefly about how things went with Astronomy Day last weekend. Very exciting annual event that unfortunately was rained out this year. Both the main date of Saturday and our backup date of Sunday were both rained out. But there was a silver lining. If we go to the next slide, please. There was an impressive amount of interest, both from club members and the general public in the event, which was very reassuring. We had, at least at the time that I called the cancellation of the event, we had 20 people lined up to come with scopes, most of them coming for the whole day, doing solar during the day and the moon and planets in the evening. We also had 6 people who just volunteered to show up and lend a hand, either at the greeting table or walking around answering questions from our guests. So that was very positive. And also the response that we've received from the public was very positive. A lot of interest in public outreach. A lot of people were very keen to participate in the event. I put some screen captures from the OAOG Facebook page there on the bottom of the slide. And you can see, we were literally engaging thousands of people through just the Facebook site alone, people interested, sharing the posts with their friends. So that was all very good news. So interest in astronomy in the Ottawa area is alive and well, and people are hungry to get out under the night sky. So that bodes well for the events that are planned for the remainder of the spring summer. Next slide, please, Chris. So in terms of what is coming up that people can put their eyes onto next, the screen just went black. There, good. Starting on the 19th of May will be the RASC star parties that are held at the Carp Library parking lot. I hope that based on the interest that we received in the Astronomy Day, that event will be very successful. In addition, the OAOG, which is mostly a group that operates in the east end of Ottawa, we're going to try to get back into our impromptu sidewalk astronomy events. So when the weather is good, we will we'll put notices up on the Facebook page of when we're going to have events. And then finally, there has been interest in perhaps considering the fall date for Astronomy Day. The U.S. Astronomical Union or League, Astronomical League, they set 2 dates per year, one in the spring, one in the fall. The fall date is September 23rd. And so we're going to look into perhaps rescheduling the spring event for the fall. So stay tuned for that later in the summer. So that's it for Astronomy Day.
I think there's links. Yeah.
Oh, sorry, there's links,
Yeah.
right.
So those will be in Astronauts as well.
Yes. Okay, great. Thanks.
Okay, thank you very much, Jim. So we're going to move on to, oh, sorry, you got some more stuff here.
I'm still going. So the poor weather that we had for the event last weekend is a good segue into what sort of tools are available to help figure out if it's going to be cloudy or not. And I have listed 3 such tools here, the 3 main ones that I use. Clear Dark Sky, a website authored by our own Attila Danko, a site called Astrospheric, and another one called Windy. And I'm going to give a quick demonstration of those 3 sites, just so people kind of have a general idea of the kind of information you can get from those 3 sites. I'm going to share my screen. So you should all be able to see my browser window now. This is the home page for Clear Dark Sky. There's a lot of tools available on this site, but the main one of interest this evening is the Clear Sky charts. So what Attila has done is created a web tool that allows forecast modeling data generated by the Canadian Meteorological Centre to be presented in a very quick to view format, and it presents 3 days of forecasting. This is an example. This is just an image at the top showing an example of what's shown, but you can see there's the top 3 rows are sort of the 3 main pieces of information of interest. The extent of the cloud cover, where a dark blue is good and white is bad. An alternative prediction model of the cloud cover, and the transparency, and sorry, there's 4. The seeing is also of use. So the transparency, so you know how much water vapor there is in the sky, and then the seeing is how steady the atmosphere is. So when you have all blue, that's good. Now you can get these charts for basically anywhere in North America. You can either enter in your Latin long, or you can do a search by name. So I'm going to search on a list for Ontario. And these are all sites that people have entered in their coordinates already, and they're kept sort of as a database. I'm going to go all the way down alphabetical to Ottawa. Look at that, home of RASC Ottawa, Ottawa Valley Astronomy and Observers Group, and Astronomy Friends. Excellent. Click. And there we go. So that's the forecast for the next 3 days in the Ottawa area. Cloud cover, transparency, and seeing. The seeing is not too bad tomorrow morning. Tomorrow morning looks like it might be good for some solar imaging. Anyway, so that's the tool for Clear Dark Sky. I like it when I'm out and I have a phone and very poor data, because it's not a very heavy data heavy site. And you can just need a browser to access it. So very handy tool. If you want to get a little bit more advanced, then you can move to Astrospheric, which presents very much the same material, the same information about cloud cover, transparency, and seeing in 3 rows, color-coded, but it also gives you some other information about the position of the sun, position of the moon, wind direction, air temperature, both wet bulb and dry bulb. And again, over three days, but then there's an extended forecast for a whole week on the bottom. There's other information about moon phases, solar eclipses, other things at the bottom. And you also get an image giving you a rough representation of what the cloud cover looks like at that particular time. And you can click at any time along this chart, and it'll give you a representation of the modeling of what the skies are forecast to look like for that particular time. And you can move your location around. Right now it defaults to Ottawa because it detects where I'm located using cookies or web magic of some sort. Figures out where you're located and tells you the forecast for where you are, but you can also drag drag this map somewhere else. If your cottage was up in maybe up in central Ontario somewhere, you could get a new forecast for that location. And there, Bob's your uncle. So a very useful tool. Bit more information about weather conditions associated with the wind. It also gives you this map, so you can kind of say, oh, okay, our sucker hole is going to move through, that kind of thing. Do a bit more planning that way. If you want to get even more advanced, then you can go to a website called windy.com. Now, this is the main page that you come to, and as the name of the website suggests, its primary function is giving you a prediction of the wind. So it's used by sailors and aviators. But it also gives you a forecast of the clouds. Over on the right-hand side, there's a toolbox. You can click on the cloud layer, and it gives you a forecast of the clouds. Now I'm going to use my mouse to scroll in here closer to Ottawa. There's a timeline along the bottom. We can move the timeline wherever we want to give us the forecast, or we can press the play button and it'll give you an animation of what the prediction is for the clouds, or whatever other layer we want to turn on, whether it's rain. You can put rain on there. You can put wind, but I primarily use the clouds. I like this site a lot when I'm really digging deep into my forecasting, because it gives 5 different models that you can choose from. The ECMWF being the most popular and the same model that Astrospheric uses, but you can also look at GFS model, HRRR model, ICON model, and the NAM model. All of these come from different various prediction groups around North America and I think Europe. So you can actually kind of compare models and see, okay, well, they're all saying things look pretty good for such a time, then you can have a higher level of confidence that it's going to be clear. And what I also like this site for is you have access to weather radar and satellite. And the satellite is kind of the final judgment, because you can animate. For the free version, you get 2 hours of satellite data that you can animate. If you want to buy a premium membership, you can get up to 12 hours. But the final proof of the pudding is looking at the satellite footage and judging for yourself, are the clouds heading my way? Are the models correct, and is it going to be clear? So that is what I use to forecast clear skies. Thank you very much.
Okay, thank you, Jim. So we're going to move on to the observations. So Richard is first up here. So let me just spotlight him. Oops. There we go.
Okay, good evening. This first picture is my view of the intermediate challenge object for the month. It's called the UFO Galaxy, or NGC 2683. I took this out at FLO, and it was a nice clear dark night. But when I got around to trying to process the picture, the outer spiral arms really didn't show up very well. So I took to heart what Andrea was telling us about last month about the special extra add-on for PixInsight called Blur Exterminator. And so I downloaded that tool and tried it out, and wow, I'm really amazed at how well that works. not only does it shrink the stars to a much more aesthetic point of light, but it really brings out some of the more fainter details of galaxies in particular. So this is my first run at using Blur Exterminator. And as I was doing this, I also noticed some other little galaxies surrounding the UFO galaxy. And I got quite interested in this little one just up and to the left of the core of the UFO galaxy. It's quite an unusual shape on the original picture. And it turns out that it's a very much more distant galaxy identified as PGC 2030408. So quite an obscure little thing, but it showed up on the picture after I processed it. Next one, please. And we haven't had a lot of clear nights this month, but one night I was going out for a walk after supper and quite defying the predictions. It was actually getting clear enough to see the moon and Venus. So I hurried back home and got out the big telescope and set it up. And just after I managed to get everything all set up, the clouds came back again. So I was very, very frustrated trying to take videos of the northeastern limb of the moon with clouds obscuring it every couple of minutes. But I did manage to catch the lunar challenge object for this month, the crater Endymion, right up there in the top right corner. But I thought even nicer in this view was the two craters just on the edge of Mare Frigidoris, which are Hercules and Atlas. They're quite prominent in the early phases of the moon. Next one, please. Now, I'm not very interested in elliptical galaxies. I find that they're not very photogenic. But so instead of taking a picture of the beginner challenge for the month, M87, I moved over a little bit. And it's a lovely time of the year for taking pictures of galaxies. This is M89 and M90. And once again, using Blur Exterminator, I found that it really brought out a lot of details in the spiral galaxy. If you move to the next picture, it's the same image with the labels. So M90 is a lovely spiral galaxy that's just slightly tilted. So it gives a view somewhat similar to the Andromeda galaxy. And then there are several smaller galaxies, more distant galaxies in the background there with IC numbers. So that's all for me this month. Thank you.
Thank you, Richard. So I'm going to turn it over to Andrea. Just give me a second here. There you go.
Can you hear me?
Yep.
Oh, good. All right. So I'm going to talk about some of my solar images that I did last month in our few days of clear sky that we had. These were two images that I took on back-to-back days. The first one, April 15th, is an H alpha with my little 40 millimeter lunt scope, and it's inverted. And it shows sort of the same sunspots that you can see the next day on April 16th. And these were shot in white light. In other words, I just shot straight through the telescope, but I use Bader solar paper that you can buy, and you can put together your own solar filter with cardboard. And you can see, next slide, please, Chris. So I ended up zooming in later on the weekend on these two specific areas, sunspot area 282, 3282, and 3280. So I wanted to highlight them. But this was a very busy time in the sun, and these regions, I think, are rotating back in the coming days. So if it is nice tomorrow, you should go out and try to take some images of the sun. Next, please. This is active sunspot region 3280, and this is a non-inverted image. And this was taken with a new setup that I recently set up, which is a quark solar filter on a 5-inch refractor. So I went for some deeper, higher resolution images than I was taking before. And I just love this because it shows all the different detail of the surface of the sun, including the dark sunspot regions, which, as Kyle indicated, were the cool areas. And you can see that filaments are also dark, meaning they are a cooler region. And the white areas are called plages, which is, of course, French for the beach, because they look like a nice white sandy beach. But they are, in fact, the very hot, bubbly, very explosive areas of the sun. Next, please. And this is when active region 3282 was just emerging. And I want to talk about what an emerging region looked like, because this is just the beginning stages of a very active region. Obviously, you can see this was an inverted image. So the sunspots are white and the filaments are also white. And you can see filaments are long streaks with prominences are also white. But what you can see, if you can't really zoom in, but there's typically 2 sunspots, and in between you see lines of magnetic flux ropes. And these are the magnetic lines that connect the 2 sunspots. And I'm going to go to the next slide, which of course Kyle has already explained, but I like this slide because it explains again how sunspots develop. Basically, a magnetic field pops up under the surface, and this is why you often see sunspots coming in pairs, because it's the magnetic field coming up one area and then going down. They often have opposite polarity as well. So I like this. Kyle already explained this in great detail, so I'm not going to spend any more time on this. But you remember that the dark sunspots are dark because they're much cooler than other areas. So that's what I've been doing with the sun lately. Oh yes, and while I was imaging one day, next slide, please. I came across a very bright area at the bottom corner of the sun. So I decided to head over there, and I did a little time lapse of a little flare exploding along the edge. I couldn't identify any sunspot region this came from, and I didn't catch all of it, but I did catch the end. And I was, again, this is with the quark, and I took a variety of short videos over about 20 minutes. And this is why solar imaging and observation is fun, because you never know when something pretty like this is about to occur. And hopefully we can do some imaging tomorrow of the sun, because it finally will be sunny tomorrow. Next, please, Chris. This is another image that I took, I think just last week. I was visiting my parents. They live in a fairly dark sky area near Lake Huron. And I wanted to try something called a deepscape image, which is where you do a deep sky object as it's rising from the horizon. So this was taken with a DSLR camera and an 85mm lens. So it's a fairly wide angle, but yet it is not a super wide angle, obviously. It's a medium telephoto. And it's with the Astro modified camera. So this is 85mm, a foreground, which is exposed separately. And then I tracked the sky as Rho Ophiuchi rose up into the sky. And I also captured the core of the Milky Way, and you can see the dark horse nebula on its side, kind of rising up. And so then I combined the stacked sky with the foreground. They were all taken at the exact same location, different times of the night. The foreground was blue hour, and then I came back and I tracked throughout the night. So that was a fun little project. I had to be up all night, and it was really cold, but I was happy with how it turned out. And that's it for me. Thank you very much.
Thank you, Andrea. So I return over to Bob Olson.
Yeah, hello. This is M87, obviously, and it's a very deep image, about 32 hours of exposure. I combined my 2021 images with my 2023 images taken last month. It's 11 nights total, plus 3 nights where my equipment or the weather didn't cooperate. Surprisingly, the image doesn't get noticeably better after about 10 hours of exposure. I'm sure it is better, but not obviously so. There's a lesson here for those imagers who spend forever gathering data. Originally, M87 was classified as a globular cluster in our own Milky Way. When you look at it, you can see certainly why. Hubble, by 1931, though, had estimated it to be about 6 million light years distance. This has obviously put it outside of our galaxy. We now calculate it to be about 54 million light years away. Next, please. This galaxy is about 30 million light years away at a magnitude of 10.6. It should be easy to see in a telescope. This is a 3.5-hour exposure. Next image, please. M57. This was one of the first objects I viewed through a telescope, and it is very easy to see. It looks like a smoke ring. When looking through a telescope, there is no color, as it is dimmer than our color vision can see. Also, we don't perceive red very well in dim light. In dim light, a red shirt would appear black. This is a wider angle image than you usually see. It looks more like the size you'd see in a telescope eyepiece. This is also a reasonably deep image. The exposure is 14 hours as a combined data from 2022 with data I gathered last month in 2023. I was imaging for 10 nights gathering the data for this image. Next image, please. This is one of the observations suggested by Oscar Echeverry. These fascinating interacting galaxies are new to me. This is probably because they were only recently discovered by William Herschel in 1787. They are about 160 million light years away. Next image, please. To me, in this rotated and cropped image, the galaxies look like a great blue heron spearing a fish with its bill. It's actually sometimes called the Heron Galaxy. Thank you.
Okay, thank you very much, Bob. So we're going to turn it over to Jim Sophia. Just give me a second, Jim, while I spotlight you. There we go.
All right. So this is a cropped and enlarged image of the planetary nebula NGC 2392, sometimes referred to as the Clown Face Nebula in the constellation Gemini, discovered by William Herschel in 1787. It's classified as a bipolar double shell nebula because in professional images you see complex shell structures around the central O-type star. Although you see a basic shell structure around the central star here. The nebula is approximately 10,000 years old, spans 50 arc seconds at a magnitude of 9.1. According to a study by Burnham in 1978, the measured radial velocity revealed that the diameter of this whole nebula is growing at a rate of 68 miles per second as the inner filaments are being ejected by strong particle winds from the central star. The outer disk contains light-year-long filaments which typically show up in photos as orange, blue, and green, or a combination thereof. The color you see is what my color camera picked up. I was using an 8-inch Smith Cassegrain telescope with a Malenkamp Skyraider camera, DS10C Tech. And the light pollution filter that I used was the Ockedahl L-Enhance filter. I took multiple exposures starting at 2 seconds and gradually progressing to 15 seconds, trying to achieve a high dynamic range of illumination so as not to blow out the core as the frames were being live stacked. And my objective was to show as much detail in the central region as possible. The stacked image was later post-processed with Topaz Studio 2. Thank you.
Okay, thank you. Just a second here. So next we have Jim Thompson. So just give me a second here. I'm There we go.
All right, thank you. So my first image tonight is of the upper right corner of the first quarter moon taken on the evening of March 29th. In the middle of the image is the observing challenge for this month, the 125-kilometer diameter crater Endymion. It is a relatively old crater as indicated by its beaten down walls and lava flooded floor. This image was captured using a monochrome ZWO ASI 183 camera, 10-inch Ritchie-Chrétien scope, and Astronomic ProPlanet 642 IR pass filter. The top 10% of 3,000 frames were stacked in AutoStacker 3 and sharpened in IM PPG. Next image, please. My second image is a mosaic of all the targets I have visited during my electronically assisted observing session on April 9th. April for me turned out to be a very productive month for observing, as I was able to get 3 good nights of spring galaxy observing in, as well as solar imaging on 3 separate occasions. These images here are all live stacks of 20-second sub-exposures, live stack 30 in total, so 5 minutes total exposure. They were captured using the same 10-inch Ritchie-Chrétien telescope, but reduced with a focal reducer to f6.5. And that was combined with a Mellencam DS432M camera and Optolong Night Sky H alpha filter. Next image, please. As I mentioned, I had a number of opportunities to image the sun over the past month. This image was captured on April 16th, a day with above average seeing in the Ottawa area. The image was captured with a 98mm refractor at f6.3, a Bader solar wedge, and a calcium K filter. It is a stack of the top 10% of 3,000 frames. I was especially impressed on this particular observing day by the extensive string of sunspots and related activity that stretched almost entirely across the lower half of the sun's face. Next image, please. This image was captured on the same day and is a composite of 2 images, one of the sun's disk and one of its prominences. The image is an H alpha view of the sun and shows in more detail the long string of activity stretching from the left side down to the lower right. Next image, please. My last image is a visual band view of one of the more complex sunspots from the same day. It was captured with the same scope and camera, but with a TeleVue 2x tele-extender added. I am very pleased with the level of detail I was able to capture from my normally very unsteady backyard skies. Thank you.
Okay, thank you. So Paul Clevenger, you are up next. So
there we go. I'm just gonna, again, as usual, cut my video to, hopefully I won't be breaking up on the audio for you. All right. All right. Well, good evening, everyone. We certainly had a few good nights since our last meeting, but certainly a lengthy stretch of awful ones as well. Looks like we got some good ones coming up next week, though, so we'll keep the fingers crossed. My first image here shows the zodiacal light that I imaged just about 2 weeks ago. You can see the Pleiades pretty much dead center of the frame, and Venus looking very bright just below the Pleiades and happening to be right in the plane of that zodiacal light. This image was taken with a 24mm lens on my Canon RP mirrorless camera and just on a stationary tripod, and was a 15-second exposure at ISO 3200. The zodiacal light, for those unfamiliar with it, is a phenomenon that's best seen from a dark site because it's a fairly faint glow of diffuse sunlight that's scattered by interplanetary dust in our solar system. It appears to extend from the sun's direction in roughly a triangular shape, as you can see here, along the zodiac, and it straddles the ecliptic plane, which explains why Venus is lying nicely in the sort of the center line of that triangle. And if my field of view had been a little bit wider, Mars would have been in the same line there, but just off the top of the frame. At our latitude of 45 degrees north, the zodiacal light is best observed in the western sky in the spring, just after evening twilight has completely ended. If you want to see this, you definitely have to get into a dark sky and wait till twilight, even astronomical twilight, has come to a complete end, because this is fairly faint. Although I must say, on the occasions that I've seen this phenomenon, it has varied a lot. Sometimes it's barely discernible. Other times it's like, oh my God, like look at that. It's so there's a number of conditions at play there in terms of your ability to see it. But the camera can usually cut it up or catch it pretty nicely. Okay, the next one, please. So yeah, this is my image of the lunar challenge object, the crater Endymion. It lies in the northeast quadrant near the edge of the lunar disk, and is 123 kilometers in diameter, and it has a depth of 2.8 kilometers. So it's quite a deep crater. I wanted to show this view because I find when the moon is in this phase, the crater itself lies right near the edge, and the mare detail, as you can see from all the mare formations, the moon becomes quite pronounced here in this phase, so long as you don't blow your exposure with too much time. Crater Endymion it's interesting because this crater's floor is relatively smooth, but it's also been flooded with an unusually dark lava. So it comes out looking almost like a small C in this view up near the top. So this image was taken with my 70mm f6 Apple and Canon 70D. It's just a single exposure of 1/124th of a second at ISO 400. Excuse me. Next one, please. All right. So one of last month's challenge objects was Messier 87. As Bob also showed us some views of this, and this particular I don't know, this particular region is my favorite galaxy-rich region of the entire sky. I mean, most of the bright objects that you see in this image are actually galaxies, not stars, and they're just a few members of the enormous Virgo supercluster. Just in this field alone, if you can throw up the next one there, Chris, there, I've thrown a few labels on there. Oh, what happened to my labels? Oh, my labels didn't show up. Oh, yes. Okay, so yeah, it may have been that your transition, the transition effects were, oh, there we are. Super. Okay, so you can see same field here, and I've labeled just the Messier objects that are in this field. Not to mention the other galaxies, for instance, those all the NGC galaxies all lying in Markarian's chain there. But just in this field alone, you've got 10 of the 110 objects in the Messier catalog. So it makes for a pretty rich hunting ground. I mean, mind you, most of these galaxies are relatively small, unless you've got a fairly large scope capable of some good magnification, because they're by and large, this portion of the Virgo cluster lies, roughly 50 to 80 million light years from here. So it's not like the Andromeda galaxy, which, relatively speaking, is pretty much next door. But M87 is of particular interest for a number of reasons there. So the next one there, please, Chris. So M87 itself, it's a super giant elliptical galaxy, and that's not me exaggerating the term. That's what it is referred to. It's a super giant elliptical galaxies, and in fact, it's one of the most massive galaxies in our portion of the observable universe here. It's also one of the brightest radio sources in the sky, and a very strong source of X-rays and gamma rays, and there's a good reason for that. the galaxy itself is 54 million light years distant and about 120 light years in diameter. So roughly the same diameter as our Milky Way. But you can see that there's no real structure in this thing. It is an elliptical galaxy. They're not known to have very definitive features, things like spiral arms, obviously. So it looks like a big globular cluster, but as Bob mentioned, it's something much more. It's much larger, and it has its own actual population of globular clusters orbiting about it, just as we have here in Milky Way. But we have about 150 to 200 globular clusters, known globular clusters orbiting the Milky Way. M87 has about 12,000. So it's a very heavy, big beast of a galaxy. But there's more to it than that, as I know many of you are aware. It has a rather interesting feature, but this feature takes a little bit of hunting because it's hiding near the very bright core of this galaxy. So the next one, please, Chris. So by toning down the exposures, I took this set that I'm showing you here with my 11-inch Edge HD and the QHY 9M monochrome CCD camera. And I took various sets at different exposure lengths to try to get past this very bright glow. You can see, I basically what I've done here is dialed down the exposure. You can see now that you're not seeing a lot of the outermost members of M87, but you can see just how bright things get as you look towards the core, because even though now most of the outer members are almost out of your visibility, the core region is still saturated. It's very bright. It's just really packed with stars. So by reducing it again, if you can show me the next one there, Chris, you can see that still as we reduce the brightness, the most of the rest of the galaxy now is not seen, but the core itself is still quite saturated. But now you're also seeing this rather a little interesting feature at about the 2 o'clock position. Dial it down again, and on the next slide, and there we have the object of interest. And what I'm going to do is I'm just going to zoom in on that with the next slide. Just bump it up a little bit so you can get a look at this thing. So this is a jet of material blasting away from the supermassive black hole at the center of M87. This jet is it's an energetic plasma being blasted out at close to the speed of light by the black hole at the center of this galaxy, and it's just a phenomenal beast. Like I don't think you'd want to live in this galaxy there, because that jet itself is about 6,000 to 7,000 light years in length, and like I said, it's being blown out at close to the speed of light. So that just can't be very good for any sort of DNA or silicon or carbon-based life. Yeah, so nice to see from a distance, but not too close. I mean, the energy is generated. The energy to create this jet is created by the acceleration of electrons moving at relativistic velocities in a magnetic field. And the next slide shows you how this is created. Oh, sorry, yeah, I should have shown you this one just to give you some scale. Remember, when I showed the original image of M87, it was showing the extent of the galaxy at about 120,000 light years across. Now we're down to about 10,000. You can see this is just in the core region, but you can see that jet quite prominently there. Next one, please. So this is just an artist's conception with a bit of an explanation to give you a view that's closer to the black hole itself. So that as you can see in the caption there, this jet is being powered by a black hole that's about 6 billion times the mass of the sun, and it lurks at the center of that very dense core. This jet is sucking in material, growing larger by the day, I'm assuming, And as this material gets sucked into the whirling accretion disk, kind of like water going down the drain of your bathtub there, it gets heated so hot that it generates all manner of other emissions, such as X-rays and gamma rays. It's just a very nasty region to be very close to because of the high energies involved. But that some of that energy does get channeled perpendicularly away, believe it or not, from the event horizon, and it creates the jets that you saw on my image there. 4 years ago, I should have added this slide, especially in light of something that I saw just 2 days ago, but I was trying to respect the deadline for a submission of observing images there, and so I didn't want to push my luck by asking Chris to answer a couple of more slides. But just for your own reference, if you go back 2 days on the astronomy of the day picture, they talk about black holes there, and it's interesting. There's in the caption itself, there's a link that you can follow that shows a thing that was just released a couple of weeks ago. It's a rework of the original black hole image that was released 4 years ago, and they've employed some artificial intelligence and other techniques to enhance that picture and to sharpen it up. And it's quite an interesting read if you want to see an enhanced version of the first image we ever got of a black hole. It's quite interesting. Just to leave you with food for thought, for those of you not too familiar with black holes and such, the black hole region is obviously that volume of space within which gravity is so strong that it doesn't even let light escape. These things are insane in terms of the physics involved. But just to give you an example of the extremities here, if you wanted to convert the Earth into a black hole, you would have to squeeze it down to less than the size of a golf ball. And you'd be left with this golf ball sized black zone around the center singularity, that is the black hole. That's if you did that with the Earth. This black hole zone, the Schwarzschild radius that you see here for M87, it's believed to have a diameter of about 4 times Neptune's orbit. So that gives you just a sense for the insane amount of mass that's been compressed into a very small volume. So again, roughly about 6 billion times the mass of the sun. Super crazy. All right, back to something a bit more digestible. My last one. I thought I'd show this one just because the study of black holes. I mean, we've learned so much in the last little while, and certainly with that picture of our first picture of the black hole a few years ago, it really kind of put icing on the cake there. I mean, what we believe nowadays is that, in fact, black holes are a normal part of formation of most galaxies. Most of the galaxies that we see that in the universe likely have black holes in them. And this is just a pair of galaxies that's close to the Virgo cluster that I was showing you. In fact, lies on the outer edges of it. This is NGC 5363 and 5364, and again, they lie about 55 million light years away in the constellation of Virgo. The spiral galaxy that you see on the right here, that's NGC 5364, and it's classified as a grand design spiral galaxy, about 100,000 light years in diameter, so similar in size to our Milky Way. And from Earth, it has from our vantage point, it has a magnitude of plus 11.2. It's relatively small. Again, given its distance there, its angular size is only about 6.5 arc minutes on the long axis. Compared to that, up at the top left corner, it's NGC 5363. It's the bright lenticular galaxy. It's believed to lie a few million light years further away than the spiral galaxy, although there's some uncertainty in this distance. It's also about 100,000 light years across and has a magnitude of 10.5. And like M87, the elliptical supermassive elliptical we were just talking about, this galaxy as well is known to have a black hole with an estimated mass of 375 million times that of our sun. So not as big as M87's, but certainly about 60 times the size of the black hole that we know resides at the heart of our own Milky Way galaxy rather. So yeah, in the field itself here, you can see several other lesser galaxies also visible, and the entire collection is related to the Virgo supercluster of galaxies. This image is actually a stack of 10 600-second exposures using the ASI 294 MC Pro camera on my 11-inch HDD configured at f7. So clear skies, folks. Looks like we may get some next week, and we'll see you again next month. Take care.
Okay, thank you very much, Paul. So up next is Oscar. Oscar, you don't have your video on, so I can't spotlight you.
Yeah, no, I can't turn my video on right now. My internet died at home, so I'm standing outside in the cold using my cell phone. So
okay,
I'll present with the video.
Okay.
All right, so I've got two images to present tonight. This first one here is of Messier 3, which is a globular cluster in Canis Venatici. It's considered by many amateur astronomers to be one of the finest globulars visible from the northern hemisphere, next to perhaps Messier 13. It's one of the largest and brightest globulars, and it's made up of about 500,000 stars. And it's estimated to be about 11.4 billion years old. And it sits about 32,600 light years away from us. It floats about 31,000 light years above the plane of the Milky Way, and it's about some 38,000 light years away from the center of the Milky Way. So that gives you some sense for its coordinates in our local universe here. It contains 274 known variable stars, which is by far the most found in any other studied globular cluster. So this particular image was comprised of 438 20-second exposures for a total integration of about 2 hours and 27 minutes. It was taken with my ZWO ASI 2400 MC Pro through my 11-inch Edge HD on the night of April 9th. Next one, please. All right, this is Messier 78, which is a reflection nebula in the constellation Orion. It's the brightest diffuse reflection nebula in a group that also contains NGCs 2064, 2067, and 2071, which are all part of the Orion B molecular cloud. The complex itself sits about 1,350 light years away from us. So yeah, it's a very beautiful and dynamic area of sky, and I really enjoyed taking this image. So this image itself is about 2 hours of luminance data and about 1 hour and 10 minutes each of red, blue, and green, for a total integration of about 5.5 hours. So this was taken with a monochrome camera, the ZWO ASI 2600 Pro, through my 8-inch Edge HD. So that's it for me this month. Thank you.
Okay, thank you very much, Oscar. So here are the observing challenges from last month. And we have the observing challenges for this month. The beginner challenge is Messier 99, a spiral galaxy. These will all be posted in our Astro Notes, so that will be coming out shortly. The intermediate challenge is NGC 4559, a spiral galaxy. And our advanced challenge is NGC 4676, interacting pair of spiral galaxies. So they're all in the same area of the sky, so good luck with those. And our lunar challenge is Crater Snellis, and it's near the southeast limb of the moon. So give that one a try. These are a summary of the observation challenges. So good luck with those, and hopefully we'll see some of these in our observation reports next month. So you may have received this email. I think it arrived just as our meeting was starting. This is a really exciting thing for RASC National. Jenna Hines, we worked with her. She was actually paramount in getting us up and running on Zoom. She left the RASC and now she is back as our new executive director. She's a marvelous person to work with. I'm really pleased that she's been hired into this position, and we look forward to working with her and try to get things cleaned up at head office. So Fred Lawson Observatory is available for use by members, and we encourage you to use this valuable resource. We have our next members only star party on May 20th. There's a waxing crescent moon, hopefully no clouds. Our first public star party of 2023, Friday, May the 19th. Rain date is the next day, Saturday the 20th. It's in the parking lot of the Ottawa Public Library, right next door to the Diefenbunker. And if you're on our distribution list, on our Google Groups distribution list, you've been asked to RSVP, so we know how many telescopes are coming. I'd appreciate if you could do that. And if you are new, you got a telescope, you have no idea how to put it together, or it's not working properly for you, please bring it along. We'll try to give you a hand with it. If you do need help with your telescope, please come before the sun sets. It's a lot easier for us to look at things when there's a little bit of daylight. So that is Friday, May the 19th. Again, we are hoping for clear skies. And then our next upcoming star parties, and these will all be published on our website. They are published on our website. They'll also be in Astronotes. So we got June 16th, July 21st, August 18th, and September the 15th. Second date is the rain cloud date for those particular events. Here are some of the folks that help keep things running along here. Our Fred Lawson Observatory Director is Rick Scholes. Estelle looks after the book library. Peter Shute is busy refurbishing equipment and looking after the Ted Bean Equipment Loan Library. Right now, our coffee and conversation position is open because we're not meeting in person. And Art Fraser looks after our membership. So I just mentioned that we've been having some meetings in the last month, and we're starting to move things forward to getting back into in-person meetings. But unfortunately, I can't give you any definitive information at this time, but I'm encouraged by the direction we are headed. So thank you. So Chris, how many did we have tonight, roughly?
We were probably about 60 people. I saw 54
60.
at any one point.
Okay. And I'm looking for topics and speakers for our June meeting. I'm giving one short presentation. Tim Cole's giving one. I've got space for another 20 to 30-minute presentation. So if you have any ideas or somebody we can contact for the June meeting, that would be great. And also for the July, August, September, October meetings as well. So we're always looking for ideas for the meetings, and I encourage you to send an email to meetingchair@ottawa.rasc.ca. So thank you, folks, for coming out tonight. And our next meeting is Friday, June the 2nd. It will be another virtual meeting. And we'll see you then. Clear skies.